Hey everyone, and welcome to The Explainer. So today we're jumping right into something absolutely fascinating, surviving Mars. We're going to strip away Hollywood's romanticized, idealized vision of the red planet and compare it directly to the brutal engineering realities and hard scientific facts that we're actually facing.
It really gets to the core of our cosmic ambitions, doesn't it? What does Hollywood actually get wrong here? We kind of have to ask ourselves, is this cinematic dream of adapting to Mars and conquering it actually achievable? Or is it just a deadly misconception that could literally cost billions of dollars and, worse, human lives? For decades, pop culture has fed us these amazing fantasies, like that classic Arnold Schwarzenegger quote, "Get your ass to Mars," or Matt Damon brilliantly farming potatoes in The Martian. We're constantly sold this frontier myth, this idea of a rugged environment, that with just enough human ingenuity and some elbow grease, we can conquer it, just like the frontiers here on Earth.
Well, let's really dive into this, because when we pivot away from the silver screen and look at the actual hostile reality of Mars, wow, the scientific truth is incredibly sobering. Exposure to the unmediated Martian environment, it isn't just challenging, it is immediately lethal. No exceptions.
Section 1, Sci-Fi Mars versus Reality. Let's get into it.
To start off, let's talk about habitats. Hollywood absolutely loves showing us these sprawling, sustainable surface settlements, right? Or a planet that's magically been terraformed so we can just walk outside and breathe the air. The reality, though? Well, terraforming would actually require increasing the atmospheric pressure by a factor of almost 200. Experts estimate that would take thousands of years, if it's even physically possible at all. And because Mars completely lacks a global magnetic field, the surface is constantly getting bombarded by extreme cosmic radiation. So actual human habitats, they aren't going to be these beautiful glass domes. They're going to be a lot closer to hermetically sealed submarines buried deep underground or tucked away safely inside ancient lava tubes.
Another massive myth is that Hollywood portrays Mars as basically just a cold desert that you can eventually adapt to. You see characters walking around with relatively light gear. But in reality, stepping outside without a highly specialized suit means instant freezing and asphyxiation. The atmosphere is literally only 1% as dense as Earth's, and it's made up of 95% carbon dioxide. You couldn't even take a single breath out there because of the lack of pressure. Oh, and with average surface temperatures hovering right around minus 80 degrees Fahrenheit, your body would freeze almost instantly.
Section 2, a lethal, hostile environment. Taking a closer look at some of these threats. Remember those cinematic potato farms we just talked about? Well, here's the catch. Martian soil is absolutely packed with perchlorates. These are highly, highly toxic chemical salts. Just to put that into perspective, here on Earth, we actually use them for rocket fuel and explosives. So Martian farming definitely wouldn't be happening in open fields of red dirt. It would require intensely purified soil, housed inside highly treated, specialized biotech labs using advanced hydroponics.
And the threats aren't just in the dirt or the air. Some of the worst ones are totally invisible. For instance, Mars has only 38% of Earth's gravity. That literally withers the human body, causing roughly 1 to 1.5% bone density loss every single month. But honestly, perhaps even more concerning is the psychological toll. Settlers would go through this Earth out of view phenomenon, where they literally watch our home planet dwindle down to a tiny speck and just disappear. The extreme isolation, the massive communication delays, and the severe sensory poverty of living in a tiny, repetitive box, that mental strain might honestly be just as deadly to the mission as the freezing temperatures outside.
Moving on to Section 3, powering the red planet. Let's see how this builds into our first major engineering solution. To survive any of these lethal threats we've covered, we are going to need an immense, absolutely uninterrupted amount of energy. So, when planning a crewed mission, NASA faced a massive, critical trade-off for their primary surface power generation. Do we rely on nuclear fission, or do we go with solar power? When you look at the data, it quickly becomes super clear why solar energy is just way too unreliable for human survival on Mars. I mean, Mars experiences these massive global dust storms that can persist for months on end, completely blocking out the sun. In fact, that's the exact phenomenon that killed the solar-powered Opportunity rover. And even on a perfectly clear day, Mars only gets about 45% of the solar energy that we get here on Earth. Combine that with a 25-hour day-night cycle, and you'd need impossibly massive batteries just to keep the life support systems running through the freezing night. It's just not viable. So, the absolutely crucial point here is that NASA officially baselined nuclear fission to mitigate that risk of mission loss.
Fission power. It doesn't care if it's nighttime. It doesn't care if there's a global dust storm raging outside. It gives you incredible high energy density in a really compact package. It easily supports the minimum 10 kilowatts needed for a small mission, and it's totally scalable to the kind of megawatt class power grids you'd eventually need for a complex, full-scale settlement.
This really brilliantly illustrates the kind of robust, life-saving infrastructure we're talking about here. It's pretty incredible to think about, right? These space fission surface power systems are designed to just operate autonomously, keeping astronauts alive around the clock absolutely no matter what Mars decides to throw at them.
Section 4. Making oxygen on Mars. Let's get into our next massive hurdle. So we have power, but we still can't breathe the air outside, and there is no way we can carry enough oxygen with us on a rocket. So how do we breathe? And for that matter, how do we fuel our rockets to even get back home? To put this into perspective, over a 2-year mission, a staggering 800 tons of oxygen is required just to supply 6 astronauts and fuel their ascent vehicle. When you consider that launch costs from Earth hover anywhere from $2,000 to $10,000 per single pound, physically shipping that much oxygen across millions of miles of space is, well, it's entirely mathematically unfeasible. No way around it.
The solution to this is just incredibly clever. It's a concept called in-situ resource utilization, or ISRU. Basically, living off the land. Researchers at the University of Calgary designed this brilliant engineering process to manufacture oxygen right there on the Martian surface, at a rate of about 50 kilograms per hour. Here's how it works. First, cryogenic cooling separates carbon dioxide directly out of the Martian air. Next, an electrolyzer electrochemically splits that CO2 into pure oxygen and carbon monoxide. And finally, to make sure you don't get a toxic buildup, a fluidized bed reactor treats that carbon monoxide with Martian regolith, the soil, to safely eliminate any dangerous byproducts. Now, what's really interesting here is the sheer scale of the economics. It is staggering. By manufacturing that oxygen directly on Mars using this ISRU process, engineers actually shrink the total system mass that needs to be shipped from Earth down to just 60 tons. In the grand scheme of things, that saves an estimated $3 billion in shipping costs. It's a total game changer.
Section 5. The true cost of survival. Let's step back and look at the big picture.
So stepping back to look at all of this, the toxic soil, the radiation, the nuclear power grids, the oxygen factories, what you should really take away from this is that surviving on Mars doesn't mean conquering some fun Wild West frontier town. It means building a fragile, incredibly expensive, highly engineered bubble. You need continuous life support, you need massive radiation shielding, and you absolutely must have multiple redundancies for every single system. Because at the end of the day, a Mars habitat isn't actually designed to let you live on Mars, it is designed entirely to keep Mars out. A single breakdown in any of these systems, it's immediately fatal. Astrophysicist Dr. Jeffrey Bennett actually sums up this reality perfectly. He says, given that we already have a world with a functioning ecosystem, it seems rather presumptuous to think we might do better starting from scratch on Mars. That's a heavy quote, right? But it really grounds this whole explainer. It perfectly contrasts our current struggles to just maintain Earth's own beautiful natural ecosystem with the sheer, maybe even arrogant idea of trying to artificially engineer a brand new one millions of miles away in a literal wasteland. So we're going to end on this final, pretty provocative thought. As you look at the absolute incredible ingenuity of human engineering, I mean, the nuclear reactors, the oxygen generators, the sheer will of us wanting to explore, you really have to weigh all of that against the brutal, unforgiving reality of the cosmos. Is mankind really meant to be a multi-planetary species? Or are we just chasing a Hollywood dream into a deadly void? Something to think about. Thank you so much for exploring this fascinating topic with me, and I'll catch you next time.